Okay, so what I would like to do just a little bit is kind of review what we did with the Kahoot. And so here's again, the denominator in the Boltzmann distribution function serves as a normalization factor. It's called the partition function. It is the total energy distribution summed across all available states. And at temperature becomes a measure of the total energy available to the system. So if we raise the temperature, we have more energy available. That means we have more molecules in the excited state. But this should be ingrained in your head. If we want to simplify the system, cool it down, and all the molecules go to the ground state, or as close as possible to the ground state. So here's a complicated graph, but let me walk you through it. So notice here that we have 3 lines plotted. Let me work on my side of things here. Okay. So Q, so this is a plot of Q right here. And then the probability for the excited state, we'll call that P1, and the ground state P0. Okay. So this is the probability of being excited. And it starts out at zero temperature. That's what we just learned, right? So we don't have any probability of being excited. Everything's in the ground state. Probability of the ground state, P0, is 1. Sure thing, 100%. Okay. But this x-axis is a little weird. It's temperature of the system divided by room temperature. So how many multiples of room temperature we have. So here we are at 2 times room temperature, and that's around 400 wave numbers. Room temperature gives you 200 wave numbers, so this is 400 wave numbers. And that happens to be the spacing of the energy levels. So right now we have enough thermal energy, to match the spacing of the energy levels. And there's about looks like a 25% chance of being in the excited state and about 75% chance of being in the ground state. So it's 75, 25. We calculated those numbers last time. Notice what happens when we go to really, really high temperatures. What are these 2 curves approaching? 50-50, right? So it's, again, both of them are approaching 50-50. So the excited state probability drops down, the ground or goes up, and the ground state probability drops down. And they get over here to the part where we have a special situation called, these are equal, right? So we have equal partition. And we use that situation so often that we've just combined those 2 words. So pretty soon when we get into talking about real molecules and so on, we'll have conditions where we say equipartition, EQUI partition. So at high temperatures, we have what we call equipartition. Now, in this situation, we only have 2 energy levels. And so we can look at this blue line, and we can say, yeah, it starts at 1 when temperature is 0. So Q goes to 1 at low temperatures. But then at high temperatures, if there's an infinite number of energy levels, it'll go to infinity. But in this case, we have a 2-level system. So Q goes to 2. So it's approaching 2 in the 2-level system. But like in a molecule, it goes up to infinity because we'll have an infinite number of possible energy levels. Okay.
How would a degenerate energy level affect that?
It's a good question. It would increase the probability of being in the excited state because you have 2 possibilities up there. And so the green curve would rise a little faster, and the red curve would drop a little sooner. Okay, so the probabilities would still approach 50-50 if we just treated the excited state as the excited state, regardless of degeneracy. So we said it's either excited or not. So then it would be a 50-50 chance. Actually, let me think about that. Since there's 2 levels in the upper state, it would be a 2/3 chance of being in the excited state and 1/3 chance of being in the ground state. But all of those levels would have equal probability individually. And so that's what we would call equipartition. Yeah. And then the Q would go to 3, since we had 3 levels. So it would go to 3. And so in this case, again, we just said that the mark reaches 50-50 at higher temperatures. And then you can just think of this. Think of Q as a count of the available energy levels. So when we're dealing with some problems later today, we're going to get into argon in a room or whatever, and there's going to be like 10 to the 30 energy levels at room temperature. So that's a huge number of energy levels that are populated. So that's it for the review on the Boltzmann distribution. So what I'm going to do is I'm going to chop these videos into smaller bits. Did I tell you all that already? Okay. So I did that for forensics too. So I'm going to chop the videos, and so there'll be multiple uploads per day. That way you can study easier. Instead of having to find the spot in a 40 or 50-minute lecture, you can find like the little review on the Boltzmann distribution would be this little 7-minute video.